Today in Lab 5, in Choose Your Own Adventure, we shall be looking at the world's largest rope swing. Today we will be investigating the physics behind this rope swing, as seen in this YouTube video shown in this link. The objectives of this lab is to relate the jumper's motion to that of a pendulum and see if the jump satisfies the energy principles. Shown in this lab is that the results were that the rope swing does follow the energy principle and it does follow a similar motion of a pendulum. The given info and the estimated info that I saw from the YouTube video was that the length of the rope is approximately 45.72 meters, and the mass of the jumper that I chose was 70 kilograms, which is the average mass of a human. The drop is 39.62 meters straight down, and at the bottom, the jumper misses the ground by 3.05 meters. And also we calculate the different degrees where it's straight down at 90 degrees and 30 degrees from the bottom of the swing. So the energy principle that we touched base on before is that delta E equals work plus the surrounding energy, and delta E equals the change in kinetic energy and the change in potential energy. Also we know that the momentum principle is F net equals delta P over delta T, which is the change in momentum over the change in time. The first thing we have to do is to calculate the speed. At the bottom, which is 90 degrees, delta E is equal to 0 since there is no work and we're not taking into account the surrounding energy. We then know that delta K plus delta U equals 0 and delta K is equal to negative delta U. Knowing the equations for delta K and delta U, we plug in that the initial velocity is 0 and the change in height is negative 45.72 meters, as we know from the rope. Then we get that the final velocity at the bottom is about 30 meters per second. At 30 degrees from the bottom, we use the same principles as before, but this time for the height, we find that the height initial is equal to the length of the rope plus the difference of the jumper from the ground at the bottom of the jump, which is equal to 48.77 meters. Also, h, the final height, is equal to the initial height minus r cosine 30, and we find that it is equal to 9.18 meters. We find that the final velocity is equal to 27.86 meters per second at 30 degrees from the bottom. Next, we find the tension. We know that F net is equal to the tension force plus the gravitational force. And from a previous lab, we know that at the bottom of the circle, the F net is equal to F perpendicular, and F parallel is equal to 0. So we know that mv squared over r equals F net, which equals the tension force plus mg, which is the gravitational force. By manipulating the problem, we get that the tension force is equal to 2058.45 newtons. We use the same method for 30 degrees from the bottom, but this time the gravitational force is different since it is at an angle, and so it's mg cosine 30 degrees. We find that the tension force is equal to 1782.45 newtons. Next we find the stretch, which we assume is 29,000 newtons per meter. To find the stretch, we set the tension force equal to the Ks, and we've solved for stretch. Stretch is known to be 0.071 at the bottom, while at 30 degrees, S is equal to 0.0615 meters. Using the code from our previous lab, we put in the initial values that acceleration of gravity is 9.81 meters per second, the mass of the human is 0.7 kilograms, and L naught, the length of the swing, or the rope, is 45.72 meters. And we know that the spring constant is 29,000 newtons per meter. Also important is to apply the momentum principle throughout the code. And we can see that we've done this by applying it to the kinetic energy and the potential energies. We put that the kinetic energy is equal to the magnitude of the person's momentum squared over 2 times the mass of the person. Another place where we apply the momentum principle is that we put that the initial momentum is equal to the magnitude of the momentum of the person, and that the momentum of the person is equal to the initial momentum of the person plus the net force times the change in time. And this is equal to the final momentum of the person, which is equal to the updated magnitude of the momentum of the person. We also update the position of the person, which is ball dot position, which is equal to the initial position plus the magnitude over the mass times the change in time. When running the code, this is what we get. It is of the pendulum moving in the direction, as well as the energy graphs. The blue is a kinetic energy, while the yellow and the green are the potential energies, while the red is the total energy, which is always on 0. Here is our graph, which is similar to that of a pendulum. The what-if question can be, what effect does air resistance or dampening have on the rope swing? Some potential energy is converted into thermal energy and cannot be converted into kinetic energy. This, in return, will lower the speed, create a smaller tension force, and smaller stretch. Overall, this lab was effective in showing the pendulum motion of the rope swing and that the energy principle was satisfied since energy equals 0 as shown by the graph seen. Thank you for watching.